Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is power factor and efficiency in AC circuits. Our objective is to explore the significance of power factor and efficiency in AC circuits, as well as compare and contrast these two properties with one another. If you've been following the AC circuit analysis playlist in its intended sequence, you'll recall that I've sprinkled several examples of power factor and efficiency throughout the previous lectures, notably the AC power examples, power in series AC circuits, and power in parallel AC circuits, all available at the Big Bad Tech channel. While not necessarily extremely difficult topics, it's perhaps worth at least a moment of our time to specifically focus our attention solely on power factor and efficiency in and of themselves without the distraction of a larger lecture. Bottom line up front, power factor is not efficiency, and efficiency is not power factor. This being said, they are related topics, and I hope to define these properties and draw clear boundaries around their individual spheres of influence and in which areas there is some overlap. Let's examine power factor first. Power factor is calculated using several different methods. Numerically, power factor is the ratio of real power in units of watts over apparent power in units of volt amperes. Additionally, power factor is the cosine of the apparent power angle. Given we are aware that apparent power is in fact not just a magnitude, but rather a complex number with both real and reactive dimensions, power factor is in effect a pre-calculated cheat code that extracts the real power component from apparent power, where real power is the apparent power times power factor. Real power is that amount of power that can actually be put to work, either heating, lifting, lowering, grinding, crushing, or moving something. What might not be obvious is that by extracting the real dimension from apparent power, power factor essentially strips apparent power of the reactive power dimension. Reactive power, measured in units of VARs, is that amount of power cyclically absorbed and returned or exchanged with the source. Reactive power, while an important property for magnetic loads like motors and transformers, doesn't actually get put to work. This is where it's helpful to think of power factor as a filter through which apparent power must pass. Power factor basically lets real power pass through and strips apparent power of the reactive dimension. Volt amperes of apparent power go in, and watts of real power come out. VARs of reactive power are removed from consideration. Power factor is ordinarily expressed as a decimal number, although sometimes is expressed as a percentage. Additionally, power factor has a flavor, either capacitive or inductive. Capacitive occasions in which current leads voltage are sometimes referred to as having a leading power factor, whereas inductive occasions in which current lags voltage are sometimes referred to as having a lagging power factor. This being said, most real-world power factor analysis scenarios involve motors, which unless explicitly stated otherwise, are ordinarily always assumed to have a lagging power factor. This default flavor often goes unstated on a motor nameplate. Finally, it should be noted that power factor can be at maximum a 1 and at minimum a 0, either leading or lagging. A power factor of 1, or unity, implies current is perfectly in phase with voltage and all of apparent power is directed towards real power and none of it towards a reactive interchange. At the opposite end of the spectrum, a power factor of 0 implies current either leads or lags voltage by a full 90 degrees and no apparent power is directed towards real power because all of it is being directed towards a reactive interchange. Let's now examine efficiency. This might be a review given your previous experience with efficiency during the DC circuit analysis playlist. Really, the only complication that AC circuit analysis brings to the table in regards to efficiency is that apparent power can be considered as having both real and reactive dimensions. Efficiency concerns itself with real power only. In summary, efficiency is a measurement of how much real power input to a system is put to beneficial use. Efficiency is calculated as the ratio of usable power out over power in and is typically expressed as a percentage. Efficiency is a very slippery fish to hold because each system defines efficiency differently depending upon its goals and intended purpose. Consider a heater with the intended purpose of heating up a vat full of some liquid. In this application, heat is the desired output and considered a beneficial use of power. In this application, there might be little, if any, losses since electrical power is readily converted into heat. Consider, however, a motor being used to pump the heated liquid into or out of the tank. In this application, mechanical power in the form of rotational speed and the twisting force known as torque is considered a beneficial use of power, and any heat produced by the motor windings would now be considered a loss. The motor's intended purpose is to not heat the liquid, but rather pump it into or out of the tank. Long story short, efficiency depends upon how one defines the system's inputs, outputs, and the intended purpose. This is where it's again helpful to think of efficiency as a filter through which real power input to a system must pass. Efficiency basically lets usable real power pass through and strips input real power of losses. Additionally, efficiency can also be conceptualized as a cascaded system, where each stage hands off a portion of usable power to the next. Consider a motor not directly driving a process, but rather indirectly driving it through a gearbox intermediary where there exists a degree of misalignment between the shaft, friction in the bearings, or backlash between the gear teeth. Conceptualized in this fashion, there is an amount of real power initially input to this system, of which electrical efficiency reduces the usable power because of losses in the form of heat. From this stage's output, mechanical efficiency further reduces the usable power output because of additional mechanical losses in the form of heat, friction, and/or noise. A multi-stage system can also be packaged as one larger system, where the efficiency of the larger system is the product of the efficiency ratings of each stage. It should be noted that the efficiency of a cascaded system is always less than the least efficient stage. If the system's electrical efficiency was 85% efficient, and the system's mechanical efficiency was 75% efficient, the entire cascaded system's efficiency would be 85% times 75%, or roughly 63.8% efficient. Finally, it should be noted that efficiency can be at maximum 100%, but only in extremely rare occasions. Ordinarily, there is always some degree of loss, although at times these losses may be considered negligible. Long story short, given losses always occur, it always takes more input power to yield a desired output power. If you ever find power output to be greater than power input, you need to immediately stop what you're doing and patent that idea, or seek reassessment of your data because it's violating fundamental properties of the observable universe. Because efficiency is such a slippery fish to hold, you'll often hear wild claims of free energy, especially in the stupider corners of the internet, often associated with terms government conspiracy, suppressed science, or alien technology. But trust me, these are outright falsehoods, or there are deceptive games being played. You can't get something for nothing. Now that we've established pretty clear definitions of both power factor and efficiency, let's compare and contrast the two. Let's start with the similarities between the two properties. Power factor strips apparent power of reactive power and leaves only real power. Similarly, efficiency strips real power input to a system of losses and leaves only usable real power output. In this sense, both power factor and efficiency can be considered as filters, letting some desirable quantity through and excluding some undesirable property from consideration. Given the similar function of these two properties, it's often best to conceptualize the interaction of power factor and efficiency as subsequent hoops through which apparent power must jump to yield usable real power output. If apparent power is to be considered the theoretical maximum, in which there is no phase shift between voltage and current, and all power is assumed to be positive, power factor is the first hoop through which apparent power must jump to yield real electrical power delivered to that device. Reactive power, while an important dimension of apparent power and undoubtedly essential to the operation of devices like motors and transformers, both of which require a magnetic field to operate, is excluded from consideration by this first power factor hoop. Efficiency, the second hoop, shaves off all real power losses like heat, friction, and noise from the real electrical power input and yields real power output. Depending upon how you define a cascaded system, each stage's output may or may not have to jump through additional efficiency hoops to yield usable power output. It should be noted that this simple model may necessitate rearrangement of the hoops or inclusion of other hoops depending upon your perspective. I'll clarify this with some examples before we close out this lecture. Speaking of examples, let's try an illustrated example. Consider a system known to consume 1 kilovolt ampere of apparent power. It has a lagging power factor of 0.9 and an efficiency of 90%. Note, despite the similar ratings, power factor is not efficiency, and efficiency is not power factor. Jumping through the 0.9 lagging power factor hoop, 1 kilovolt ampere of apparent power yields 900 watts of real electrical power input to this system. The 435.9 bars of reactive power, while essential to this system's operation, is excluded from consideration by power factor. When 900 watts of real input power jumps through the 90% efficiency hoop, it yields 810 watts of usable power output, where 90 watts have been lost to heat, friction, or noise. In summary, 1 kilovolt ampere of apparent power comes in, and 810 watts of usable power comes out. This chain of calculations should be relatively self-explanatory. Let's now examine the differences between power factor and efficiency. First, power factor concerns itself with both apparent and real power. In contrast, efficiency concerns itself solely with real power transfer through a larger system. Additionally, there is a stark difference between the numerical calculation of power factor and efficiency. Given this example system has a 90% efficiency rating, also implicitly implies that this system is 10% inefficient. Power in must equal power out. This implies that all power must go somewhere, and if it's not usable, it's considered a loss. Given 900 watts of real power is input to this 90% efficient system, 0.9 times 900 or 810 watts goes to usable power, and 0.1 times 900 or 90 watts is considered a loss. No such linearity exists with power factor. Recall that apparent power is a complex number consisting of both real and reactive dimensions. Yes, a lagging power factor of 0.9 implies that 0.9 of 1 kilovolt ampere or 900 watts is input to this system, but it most assuredly does not imply that 0.1 of 1 kilovolt ampere or 100 VARs goes towards a reactive interchange. Long story short, real and reactive power do have a give-and-take relationship, but it's not linear. Recall that real power in units of watts is apparent power times the cosine of the apparent power angle. Reactive power in units of VARs, in contrast, is apparent power times the sine of the apparent power angle. If one knows the power factor, one can calculate the apparent power angle by taking the inverse cosine of power factor. This angle can then be used to calculate reactive power. For this particular example, the inverse cosine of 0.9 is an apparent power angle of roughly 25.8 degrees. The angle is assumed to be positive because we're clearly dealing with an inductive occasion in which current lags voltage and inductive reactive power is assumed to be positive. Substituting in our given values yields not 100, but rather 435.9 VARs. As a follow-on exercise, consider how power factor and efficiency not only influence each other, but also the final result. For this second iteration, let's say power factor remains 0.9 and efficiency is increased to 95%. If this system continues to consume 1 kVA of apparent power, jumping through the power factor hoop, the input real electrical power is 900 watts as previously. The 435.9 VARs of reactive power, while essential to this system's operation, is excluded from consideration by power factor. When real power jumps through the increased efficiency hoop, it yields 855 watts of usable power output, where only 45 watts have been lost to heat, friction, or noise. Compare and contrast this implementation with our previous one. The same amount of real power went into the system, but more of it came out because it was used more efficiently. Let's come at this from a different direction this time, increasing power factor to 0.95 and keeping efficiency at 90%. If this system continues to consume 1 kVA of apparent power, jumping through the power factor hoop, 1 kVA of apparent power yields an increased real power input of 950 watts. Taking the inverse cosine of power factor demonstrates the apparent power angle is 18.2 degrees. The 312.2 VARs of reactive power, while essential to this system's operation, is excluded from consideration by power factor. When real power jumps through the efficiency hoop, it also yields 855 watts of usable power output, only this time an increased amount of 95 watts have been lost to heat, friction, and/or noise. Let's compare and contrast these three implementations with one another. For our third implementation, an increased power factor of 0.95 resulted in not only more real power input into this system, but also less reactive. This being said, Given efficiency remained at 90%, the third implementation used the increased amount of real power input as wisely as the first. However, given the system had more real power input to it in the first place, it resulted in the same amount of output power as the second implementation. Additionally, note the third implementation resulted in more losses, in this case 95 watts, more than double the losses of the second implementation. This implies that the third implementation might require a more robust, i.e. heavier and more expensive frame or heat exchanger to dissipate these increased losses. Again, all power has to go somewhere, even if its destination is considered a loss. One cannot expect even a 99.9% efficient gearbox designed to handle 2 megawatts of power to be made out of tissue paper and compressed cheese. 0.1% losses of 2 megawatts is still 2 kilowatts, or 2,000 watts, and this 2,000 watts needs to go somewhere via a sufficiently robust channel. Now that we've got a pretty clear understanding of power factor and efficiency, let's put your understanding of these properties to the test with this series of illustrated example problems. For each scenario, use the given data to fill in the missing information. Some of these scenarios may take some thought and effort on your part. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first illustrated example problem features a system consuming 2 megavolt amperes of apparent power at a lagging power factor of 0.8, driving a 75% efficient system. We're being asked to solve for real power, reactive power, losses, and usable power output by this system. This is pretty easy considering it's a direct repeat of our previous examples. A power factor of 0.8 implies an apparent power angle of roughly 36.9 degrees. This implies power factor excludes approximately 1.2 megavars of reactive power from consideration, meaning only 1.6 megawatts of real power is considered input. Of this 1.6 megawatts of input power, the 75% efficient system outputs only 1.2 megawatts of power considered usable, and 0.4 megawatts, or 400 kilowatts, is considered a loss. Our second illustrated example features a two-stage system producing 2 horsepower of usable power. The first stage of the system is known to be 75% efficient, and the second stage of the system is known to be 85% efficient. Additionally, we're aware the system has a lagging power factor of 0.84. We're being asked to solve for the apparent power, the real power, the reactive power, the losses in stage 1, the usable power output of stage 1, which coincidentally is the power input to stage 2, and finally the losses in stage 2. This is essentially the same problem as previously, only it uses 2 stages and it's being done in reverse. First, we need to do a unit conversion. 2 horsepower is equivalent to 1,492 watts. Given 1,492 watts of usable power is coming out of the second 85% efficient system, means 1,492 divided by 0.85, or 1,755.3, or roughly 1.8 kilowatts of power was input to it, and approximately 263.3 watts is considered a loss. Power input to this stage is greater than the power output, not the other way around. Similarly, 1,755.3 watts of usable power output is coming out of the first 75% efficient system, means roughly 2,340.4, or approximately 2.3 kilowatts of real power was input to it, and approximately 585.1 watts is considered a loss. Again, power input is greater than power output, not the other way around. Given 2,340.4 watts of real power is being input to this two-stage system with a lagging power factor of 0.84, means the system is consuming 2,786.2 volt amperes, or roughly 2.8 kilovolt amperes of apparent power, of which 1,511.7, or approximately 1.5 kilovars of reactive power is excluded from consideration. Finally, our third illustrated example problem features a system known to produce 400 watts of usable power. We're additionally aware that the system is consuming 600 volt amperes of apparent power and positive 250 vars of reactive power. We're being asked to solve for power factor, efficiency, real power input, and losses. This isn't a complete setup as were the 2 previous example problems and might have necessitated some thought and effort on your part. Given reactive power is apparent power times the sine of the apparent power angle, we can rearrange this equation to solve for the apparent power angle. where the apparent power angle is the inverse sine of reactive power over apparent power. Substituting in our given values yields an apparent power angle of 24.6 degrees. Given the cosine of the apparent power angle is power factor, we can substitute our given values to solve for power factor. Cosine of 24.6 degrees yields a power factor of roughly 0.91. Given a known apparent power figure and a known power factor, we can solve for real power, where real power equals apparent power times power factor. Substituting in our given values yields a real power input of 545.4 watts. Given 400 watts of real power output implies this system has a 400 over 545.4, or approximately 73.4% efficiency, and approximately 145.4 watts of power is considered a loss.